Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of solar data from various time periods. So we have different times and a bunch of different metrics about the sun and the weather, and we're going to try to predict the solar radiation from a given period. And for this, we're going to be using XGBoost, which is a gradient boosting library that will give us much better results than a standard linear regression model. So let's import NumPy and pandas to start dealing with the data, and then we'll use the standard scalar and train test split function for pre-processing, and that's from sklearn. Then we'll use Optuna to find the optimal hyperparameters to use within our XGBoost model, and then we'll import XGBoost as XGB. Afterwards, I'm going to get the R² score, so I'm just importing that from sklearn.metrics. Let's go ahead and import that, and then we'll load the data in using pandas.readcsv, and we'll get the file path right over here, copy file path, paste it in, and then we'll take a look. And we have 11 columns and 32,000 training examples. And what we want to do is predict this radiation column. So let's start by getting a little information about what's going on under the hood. So data.info is going to give us the null values and the data types. And by the looks of it, there are no null values, which is really good. So let me just double check, just to print. I'll print out total missing values, and then, whoops, I will, at the end, I will print data.isNA, which will give us the data frame of all true or false values, whether a given value is missing or not. And I'll sum across the rows to give us the number of missing values in each column. And then I'll sum across the columns to give us the total number of missing values in the whole data set, and that is 0. So we don't have to worry about missing values. That's really good. So let's start feature engineering. And so what I mean is we have a lot of these date and time columns. Here are some times. Here's date and time in one. And here's just a time column on its own. Those are currently not very useful in their current state because, well, for example, we could sort them in terms of recency, but the problem with that is that we don't account for cycles, and that's what the month is really good at giving us, is a cycle of the year. We can use the year to give us a strict value of like recency, and then the month will tell us what time of year, was it hot or cold. I'm actually going to use the day as well, just because it's nice to have that extra feature, although usually I don't use the day. And then this Unix time feature, this is actually, if you don't know, it's the number of seconds since January 1st, 1970. So this is a very nice way of sort of giving us an ordinal feature for time. It just is straight up how recent was it relative to other examples. Alright, so let us start by, actually I need one more import before we go. I'm going to import regular expressions, RE. And the reason I'm using regular expressions here is because you see how these date values are not perfectly lined up. See that this isn't 09, it's just 9. So it's actually not the same number of characters as when there are 2 digits. So in order to target for certain aspects of the example, I'm going to need regular expressions. So the way we can apply a regular expression, let's deal with this data column first because it's the big one. We have data sub data, which is just all these dates and times, times and dates, dates and times right next to each other. And we can apply a lambda function to it that will take in some x and return some value based on x. And so x would be a single one of these. So we want to use some regular expression on x that's going to match certain aspects of the string, which is for what we want. So we can use re.search to search a regular expression in x. So this is just a raw string, and I'm going to put the regular expression inside that, and it's going to return matches that it finds in x according to the regular expression. So let me grab one of these training examples, and then I'm going to head over to regex101.com, which is a great free platform for testing out regular expressions. So I'm going to put the test string right in there, and then we can type in regular expressions up here to try to capture what we need. So let's try to first we'll deal with the month. Let's just get the month off there. So the easiest way to do this would be a caret to mean beginning of the line, and then \d for a digit character, and then plus to mean a digit character any number of times, until we hit something that is not a digit character, which will be the slash. So this is all we need. Copy that, I'm going to go back in, and I'm just going to paste it right in there. And now, if we look at what this looks like, there's one more thing I have to do actually, which is after we search, it'll return a regular expression match object, and to get the string version of that, I have to call group on it, group of 0. And so if I run that, you can see we now have all of the months right here taken off of the date column. So what I'll do is I'll just make a new column called month. Next, we'll do a very similar thing, but now we're going to get the day, which will just be this value, these two. And sometimes it's 1 as well, so we still, again, have to use regular expressions here. And this one, we might need a little more complicated regular expression. Now we're going to delete that. We want to get this guy, just the 2 and the 9 here. So I noticed that it's separated on each side by a forward slash. So we can use something called a positive look behind and positive look ahead expression to capture the 29. And so what that looks like is this, and I have to fill them in. So the positive look behind means look behind the string and see if something exists there. And so this is the format. It says look behind a certain character, and the character we want to look for is a forward slash. I'm using a backslash to match the forward slash literally, and that's noticing it's now targeting everything that's after a forward slash. And we want digit characters any number of times, and then we want to make sure there's also a forward slash on the other side of it, so we will use a look ahead expression like this, and with another forward slash. Only difference here is there is a less than sign in the look behind. So you'll notice that this now matches just the 29. So we're going to grab that, we're going to put it in here, and now let's just take a look at this without actually applying it to the column yet. We're just going to run that line of code, and you'll see we have 29 at the top and 1 at the bottom. So this is just the days. And we're going to do one last one, which is the year. So we want just this value. So let's go back into here, and let's worry about getting this 2016 value. Now, I noticed that it's always followed by a white space character. So what we could do, let's see, I guess what we'll do is we'll keep the old regular expression, except instead of matching a forward slash on the right side, we're going to match white space. The way to do that is just replace it with \s for white space characters. So that will match our year. We'll grab that and we'll put it in here. Alright. And now if we take a look at this, just running that code, you'll see it's all the years. Okay, now before I actually apply these, I'm going to cast the columns into NumPy integers, just so that we're not dealing with strings anymore. And then when it's done, we can actually drop the original data column because it's no longer giving us useful information. You'll notice that this time here it's just 12 a.m., which isn't helpful. We have an actual time column here, so we're not going to worry about that 12 a.m. So we're dropping data from axis 1, and we have that new data. Now if we look at it, you'll see the original date column is gone, and we now have month, day, and year. If you compare it here, it's just the 9 was taken, the 29 was taken, the 2016 was taken. So here's the original column split into 3. Alright, so now let's deal with the time column. And now we have the idea, we can just copy this and modify it. Instead of dealing with data here, let's let's just highlight all of these, and we'll replace it with time, because now we're dealing with this column. And we don't need these regular expressions anymore. I'm just going to remove them. And now we need some new ones. Also, this is not month, day, and year, but rather it is hour, minute, and second. Even though I don't really know how much value we get from a second feature, but we're going to use it anyway. Okay, so let's grab one of these, and we'll put it in regex 101. Get rid of that white space, and let's try to target just the hour. So this is a lot simpler, actually. All we need is to do beginning of the line with a caret, and then digit characters any number of times, and that will just capture the 23. So I think that's actually what we had before, right? For the first one. Alright, for the second one, we may need to actually use a look behind again in the similar format, like this. Just copy that out, put it in here. Except instead of looking for backslashes, we're just going to look for colons, and that will give us the minute. All right, and then oh no, I put it in the wrong one. It should be here. Okay, we're good. And then the last one is not as difficult. We can actually specify end of the line with a $, and then look for digits before it, and there we go. All right, and now this is hour, minute, second, taken from the time column with the following regexes, and we're going to drop time when we're done, and we're also casting them into integers. Let's take a look. You can see the hour, minute, and second have been taken off of the original time column. 23, 55, 26 came from there. Okay. So, two more columns here we have to do this for, which is just time sunrise and time sunset, but that's exactly the same thing as we're due with this one. However, you'll notice that these ones do not have second data. They just have hour and minute, so we don't have a need for the second. And we're just going to copy it twice, and then we'll call this, here I'll put it like this, sunrise hour, and these will be sunrise hour, sunrise minute, and this will be sunset hour, sunset minute. And then we can remove that, and then at the end we're just going to drop, what is this? Time sunrise, time sunset. Alright, and now we just have to change these columns, and we should be good to go. So this is time sunrise, and these two down here is time sunset. Alright, and that should give us what we need. So take a look at data. You can see the sunrise and sunset now have their own columns, 6 and 13, 8 and 18, 13. That's from 6 and 13 and 18, 13. Alright, and now you'll notice that everything is in nice numerical form. We can verify this just by checking the data types of the data, and you'll see everything is either integer or float. So let's move on to splitting and scaling the data. I'm going to start by creating an X and Y, and I'm only going to use these temporarily because I'm going to use here. I'll just do it and I'll explain it. Let's create a Y, which is what we're going to try to predict. It's going to be the radiation column, like I said earlier. So just the radiation column, but we're going to make a deep copy of it stored in Y. And X is going to be everything except the radiation column. So this is effectively performing a split on the data, splitting what we're trying to predict from what we're going to use to predict it. And we'll make a copy of that as well. Alright, now I'm going to create a new scalar object. This is a standard scalar from sklearn. And what this is going to do is it's going to take X, which is all our features, so everything except for radiation, and on each column it's going to scale the column to have a mean 0 and unit variance. So X is equal to scalar.fit transform X. Alright, and now if we were to look at X, let me just turn it back into a data frame so we can see. It's like before, Don't mind the column names; they're gone. But you can see that each column has been scaled so that they take on very similar values. This is interesting. I notice they're all zeros here, which may mean that we have all the same value. Let's check out the year column. So data sub year dot unique. Okay, there's only one value in year, which means this is a useless column. So let's drop it. Let's drop the year. In fact, we don't even need this in the first place. Should we keep it? Because it's good practice. Yeah, we'll keep it. We'll just drop it down here. Let me move this unique thing. Where did I put that? Did I delete it? Okay, I'll put it here. Data sub year dot unique, and then data dot drop year. Alright, now let's recreate our y and x from data. Now we'll scale x, now we'll check x, and you can see we don't. Oh, we have another one. Did I not notice that? What is that, sunrise hour? Okay, let's try this. Data sub sunrise hour dot unique. Yeah, there's just a 6, so we're going to drop them both. Okay, I'll do this sunrise hour drop, and then I'm going to put year in there as well. Alright. Now, let's check this one more time. No, we have to recreate x and y, sorry, then scale it, then check it. Now we have no zeros. Okay, we're good to go. Sorry about that. Okay, so now let's split it into train and test sets. So I'm actually going to create a train, a test, and a validation set. And we're going to start by creating train and test. So x train, y train. X train, x test, y train, y test. We're using the train test split function from sklearn to split x and y to give it a train size of 70%, and we'll include a random state of 100 just to reproduce the results when we're done. Then after that's been split, I'm going to split the train set even further to get a validation set. So x train, x val, y train, y val equals train test split. This time we're splitting on x train, y train. And we'll give a train size of 80% because we want 20% of the training examples to be used as validation. Random state, 200, why not? Alright, and then we now have these 6 different subsets of our data. If we look at the shape of them, let's see, x train dot shape sub 0, so number of examples if we do 0. Now let's do it for validation and test. So we have 18,000 examples in our train set, 4,500 in the validation, and 9,800 in our test. So very good. Now we're going to turn them into something called a D matrix, which is a data type that XGBoost uses to optimize performance. So we'll call it dtrain, dval, and dtest. They contain both the x and y in a single format. And we'll do xgb.dmatrix of xtrain, and the label will be ytrain. Similarly, we can do that for this and this, but this will be xval, and this will be yval, and for here we'll have test. Alright, so now we have 3. You see they're actually just dmatrix objects, but they contain the data, both the training set, both the features and the label in one format. So let's train. So I'm going to use Optuna to optimize the hyperparameters. And the way Optuna works is we have this objective function that Optuna tries to minimize. And it takes in a trial, that's an Optuna object. And we want to specify all the parameters we want to tune. So the parameters I want to use is going to be the learning rate, the max depth of a tree in the gradient boosting, because it uses we're going to do a tree boost, and then L1 regularization, L2 regularization strength. Alright, and then at the end we'll create this parameter dictionary that will map a name, which is, let me see something. Yeah, okay. The name is important. The name has to be the same name that what's it called? That XGBoost is going to take. So learning rate, the value for it will be given by learning rate, which we're about to define in a second. The max depth is going to be given by max depth, and then alpha is what the L1 regularization is called, and lambda is what the L2 regularization is called. Alright, so it's going to be a dictionary that maps a parameter name to a parameter value. And we're going to define the parameter values up here. So learning rate is going to be trial, which is this thing that we're passing in up here, dot suggest, let me do it with max depth first, because it's easier to understand. Trial dot suggest int max depth for 8. So what this means is it's going to pick a random integer between 4 and 8. And that's going to be for the max depth value. Now, suggest it's going to call 100 trials, or any number of trials that I want. But each time it does a new trial, it's going to suggest a new integer, and so we're going to get this random bouncing around of parameters, and it's going to try to find the best parameters this way. So for the reason I did the second is because we don't want an integer for the learning rate. We want something drawn from the log uniform distribution, which will give continuous values, but with most of the values centered around lower numbers. And that's good because the learning rate is more sensitive to change at the lower values. So we'll draw values from between 0,0001 and 10. And it'll just bounce around, but most of the bouncing will happen towards the bottom half. That's why we do log uniform. Then these two are also log uniform. Regularization strength also is more sensitive at the lower values. So this will be L1 reg. These names don't really matter. This is just for Optuna. Alright, and then we have these parameters that take values from these suggested values, and we're going to return okay, I haven't written this function yet. Get model RMSE of params. And so what this objective function does is creates these new parameters and then tests them out and gets a loss value. And it's going to keep trying new parameters until it finds the least loss value. So let's now create this function get model RMSE. And it's going to take in a set of params that we're going to pass in, right? We pass it in. Here it is. Where it's going to create a new model, which will be xgb.train. And we're going to pass in params to this. So these are parameters that are actually being used to train the model. And we're training it on dtrain, which is this D matrix up here. Alright, we'll specify a number of boost rounds. 100 is good. And then we'll specify the validation set as well. Evals equals, this takes a list of tuples for validation sets. Dval is our validation D matrix, and we'll call it eval. And then let's also give it an early stopping functionality. So if it doesn't improve after 10 rounds, we'll stop early. Okay, and I'm just going to turn off verbose mode. Verbose eval equals 0. Alright, so it trains the model, and then we're going to store the results in results using model.eval dtest. So we're going to evaluate it on the test set, and then get the lowest hyperparameters for that. I'm wondering if we should use the validation set here. I might use the validation set. Nah, I'll just use test set. But it's usually best to keep the test set untouched until the end, because technically we're biasing the model by picking hyperparameters that work on the test set. So you know what? Yeah, let's just do it on the validation set. All right, then we'll get the RMSE, which this is very peculiar to me. Results ended up returning. All right, so let me see. Here, let me show you what I mean. It's hard to explain this. Let's just return results. And I'm going to just create a test model, get model RMSE, and the parameters I'm going to pass in, what we'll do is params equals, it'll be this thing. But I'm just going to give it like dummy values. Okay. So I'm going to pass those params in here just to show you what a model.eval returns. NumBoost round. Oh, it should be round, not rounds. Okay. So here's the RMSE value, and it returns it in this weird sort of string with a tab character and then eval RMSE. So I wasn't really sure how to get just the float value out of it, so I ended up just using regular expressions again to target anything that comes after any digit characters at the end of the line. So over here, what I did was RMSE equals re.search, like we did earlier. We're searching a regular expression in the results string, which looks like this, and we get the groups of 0 afterwards. And we're going to search for end of line, and then before end of line, digit characters. However, digit characters do not count periods, so I'm actually going to enclose this in a group and count digit characters or a period any number of times. And this will this will give us the RMSE value, and then I'm going to cast it to a float after that. Yeah, that's really annoying, sort of hacky workaround, but if anyone knows how to just get the float, please tell me. Alright, so we'll run that, and then we don't need this anymore. Now we have this objective function that's going to try out this function with a bunch of different parameters, and each time it's going, sorry, this should return RMSE. Each time it's going to get the RMSE value for that set of parameters. So, let's now create a new study, which is an Optuna object that performs this kind of testing of parameters. Optuna.createStudy, and we'll say study.optimize. We'll pass in objective. That's this function here. Number of trials, we can do 100. Not really, doesn't matter too much. And we'll just do show progress bar equals true. Alright, now this will take a moment, so I'll just pause the video and come back when it's done. Alright, so the study finished and ended up getting best trial is trial 88, it said. So let's get the best parameters. We can get study dot best params, and so these are the best parameters it found, which is great. So let's call this best params, and then I'll just put it again there. Okay. So now let's create a final model. This is going to be our real model. That's going to be xgb.train best params. We're passing in dtrain, and the number of boost rounds will be 100. No, actually, it's going to be much more because I want to make sure we converge. So 10,000, and passing the validation data. So it's going to be dval and eval, like I did before, and then early stopping rounds 10. Alright, now we're going to actually train this real model, and I don't know how many this will go for. It stopped after 101 as it started going, the RMSE started going back up again. And now let's create some predictions. So y_true is going to be the actual values of our examples, and we're just going to take our y_test, which is from our original test set, and we're going to make it into a numpy array. And we'll just specify the data type as numpy.float. So if we look at what this looks like, it's just an array of all of our original radiation values up here as a numpy array. So that'll be y_true, and then y_pred will be our predictions, which we'll get from model.predict. So this is an XGBoost function that can predict on a test set, and we'll pass a dtest, and we'll also turn that into a numpy array when we're done with dtype numpy.float. Alright, if we look what this looks like, you can see it is a bunch of predicted values. So we run that, and let's check the results. I'm going to create an r² value from the r2 score, r² score from sklearn. You just pass in y_true and y_pred, and print out the result. So r² score, I'll format the string here to have, we'll show 4 decimal spaces. Dot format r2, and we end up with an r² score of 0.94, which is pretty good. You know, that's pretty good. I'm sure we could do better. This is by no means an exhaustive, like absolute perfect model. This is just to give you a demonstration of XGBoost and Optuna and the power of using this kind of these libraries to improve regression tasks. So that will conclude today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.